Hey folks, let's go ahead and get started with the lecture. Please don't make me try to have to shout over you because my voice was going to go out. I have a bit too many lectures in my life to do that. Okay, so quiet on down. Don't make me shout over everybody talking. If you want to talk, then you're going to want to leave and I'll take you off the attendance. Okay? All right, so this is TMS right here. That's that tetramethyl, excuse me. Did I say trimethyl before? Yeah. Tetramethyl silane. And that has a chemical shift of 0. So that's what you measure every other chemical shift off of. And that actually right there, is that ever have any error in it? No, but because by definition, that's your 0, isn't it? Everything else has error on it. Okay? Okay. And so this then would be your different groups and the sort of chemical shifts you'd expect to see. So this right here would be a methyl on a normal alkane, right? And so you should expect those to show up at about 0.9. They usually show up just a little bit under 1. Okay, so the 0.9. And then what you see is anybody remember the name of this one, by the way? This is the methylene. Okay, it's the CH2s in between, right? So in an alkane, the CH2s in between, those always show up at 1.3. Notice that you have less shielding on this methylene because it has less hydrogens to put electrons into the carbon, right? Whereas the methyl group has more shielding because it has more hydrogens to put electrons on that carbon, okay? To help donate electrons onto it. This right here would be a tertiary one. Notice that's 1.4. You actually get less effect from that, and so it has a smaller difference from the shift. It's a larger shift. It's 1.4 instead, though. Okay, and so this one right here is your triple bond. Notice you actually get a pretty good shift here. So this would be the terminal alkyne. Can we have a central alkyne in a HNMR? No, we can only have a terminal, right? Because it detects the hydrogens off these, right? And there's no hydrogen if this was carbon, right? Okay. All right, so this is when we're trying to start seeing the effects of functional groups, okay? So here we have a bromine that's attached to a methyl. So instead of it being a carbon here, it's a bromine. And that's going to give you a shift of 2.7. This is because of the heightened electronegativity of the bromine, right? And so you're seeing the bromine pull electron density away from the carbon here, and thus pull electron density away from the hydrogen that's attached. This right here is a chlorine, and what do you notice about the shift? Larger shift, right? So 3.1, and again, that's because it's more electronegative than the bromine, isn't it? Okay. All right, and so here we have an oxygen. It's attached between either two carbons or a hydrogen here. So the oxygen is attached to the carbon where our hydrogen is located. And what we notice here is, again, oxygen has a fairly similar electronegativity as chlorine. And so we get a pretty similar peak, don't we? Yeah, just a little bit higher. Okay. And so that gives a chemical shift of 3.3. Now, right here we have a benzene. Ooh, that's a high shift. What's going on there? Really high shift, right? Mm-hmm. Kinda. Yeah, so it has a full ring resonance, right? It has a conjugated ring, and so that conjugated ring is a wire, isn't it? It's like putting a little wire into a magnetic field. Anybody know how you generate electricity using steam, like all electricity that's generated and used, or how like an electric vehicle works? If you move a wire within a magnetic field, it actually generates electricity, moves electrons. Or another way of saying that is electrons moving in a circle, like within a wire or an aromatic system, right? Actually generates its own magnetic field. And so what you're actually seeing here is the effect of its own magnetic field countering the magnetic field of the system, right? Okay. And so for things that are conjugated and aromatic and double bonds and triple bonds, you can actually see magnetic fields either opposing which is destructive interference, or adding, which is constructive interference. Okay? Because their own magnetic fields can line up with this. Neat, huh? Yeah, so you get a huge effect here. It's one of the largest effects. You have to put a lot of oxygens on to get something like this. Okay? So it's actually these aromaticities with these double bonds give you some of your largest effects possible. And of course, when we look at carbonyl, that has a double bond that also has an oxygen, right? And so you get a particularly large shift. Okay? And so you get somewhere in the 9 to 10. This one actually varies a lot depending on geometries. So this is the first spot where you're going to see a lot of range to these things. Okay? And part of that is, again, you have things like hydrogen bonding that are possible. You also have geometry differences that are possible. Okay? And so you get more states that are possible, right? So you can get differences here. Okay, so that's going to be a carbonyl right there. The hydrogen that's off of it, that would be an aldehyde, right? Would this ever be a ketone that we would see here? Yeah, no hydrogen there, right? Yeah, the ketone has a R there, doesn't it? Okay, and so that's somewhere between the 9 and 10 usually. This one right here is your amine. So this right here is a primary amine, and that's going to have that hydrogen showing up somewhere between 1.5 to 4. This one actually has quite a bit of variability. Okay. This is your alcohol hydrogen, and again, this is going to have quite a bit of variability, but it's going to have fairly pulled away deshieldeds. And so 2 to 5, a little bit higher than the amines usually. All right. Okay, so this is the next one over. These are the alphas. Is everybody okay with that terminology, alpha? Anybody remember alpha? Okay. Yeah, there's my functional group, right? Alpha, next one over. Excellent. Okay, so these are going to be on the alpha carbons, and they're going to be the hydrogens on the alpha carbons. And so what you're going to see is you're going to get a same sort of patterns overall for most of these, but we're going to see a drastic reduction in that pattern, okay? Because it's no longer, for example, if it's attached to something very electronegative, it's no longer the one that's right next to it and getting pulled on the hardest, right? It's the one off that, and so it's getting a lot less pull on it, right? It's getting a lot less of the electron density pulled away, okay? Okay, so here we see our double bond. That's going to be a chemical shift of 1.7. So that next hydrogen over is going to be a 1.7. If you remember from our previous slide, which is not letting me go back. Okay. I didn't have the double bond. Anyways, here's the carbonyl, the next one over. So this right here would be a thing like a ketone, right? So that's a ketone. And that's going to be a 2.1. Okay, notice again that's a lot less shift than the other one, right? That was directly attached. This is the next one over from a benzene ring, and that's only a 2.3. That's a huge drop off, right? And that's because you're no longer next to the wiring. Okay? Kind of like when you're in a house and you're under power lines, right? Like, people don't mind being the several houses over from power lines. Nobody wants to be the one under the power line, right? Okay, same effect here. This one right here is a fluorine, and so you're seeing a fluorine, which is the most electronegative thing you're going to see attached to these, and that's actually the most polar, right? And so we get the most deshielding, okay, or the largest chemical shift of a direct electronegative effect. All right, and so this is your double bond right here. If you go ahead and look at those versus each other, that's a pretty big difference, isn't it? And so you see a 4.7, and again, that has to do with the pi bond, because again, that electrons that can move around are going to have a magnetic field of their own. Okay, this is another double bond here, and we can see this one is 5.3. The difference being this one has hydrogens on this side, right? This one has a methyl on this side. So that adds a bit more electronegativity there. All right, this right here is going to be an aromatic ring off of an OH. And so that would be like your phenols, that sort of thing. And Again, it doesn't have the sort of shift that you would have seen in just right off an aromatic ring because you're not directly under that wire, right? Yeah. But you do have a pretty good shift because of the oxygen, and then the oxygen has those conjugate states, right? Okay, and this is going to be a carboxylic acid, huge shift, and the reason for that is this right here is not actually fully a single bond, is it? It can actually have some of this character mixed in. And so you get both the electronegativities pulling electrons off, and you get this system where you actually have a little bit of conjugate behavior. Okay, so it's actually an extremely electron poor hydrogen, right? Also, it's normally an acid, isn't it? Carboxylic acid, right? And so it's very deshielded. You actually know that because it usually like leaves as H+, right? So that tells you it has very little of the electron density that actually stays on there. Yeah. Okay, so this right here is your BEFF, your effective magnetic field, and the delta E, the energy difference for those spin states. So as you increase your effective magnetic field on a system, what's going to happen to those energy states? So if you have a weak magnet, what's going to happen to those energy states to shift them? Let me put it another way. Okay, I get a little tiny fridge magnet. How easy is it to pull that off? Very, yeah. I get one of those magnets that lifts cars. How easy is that to pull that off? And so the energy went up, right? Okay? And you're experiencing the same thing here, aren't you? You have this magnetic field. It's aligning these atoms so that they are the correct poles within that magnetic field. To flip those is going to take more energy, the more powerful the magnetic field, right? Now remember that what actually matters here, though, is not the power of your magnet necessarily, right? That's not the only part that matters. What matters is the effective magnetic field that your atoms are actually experiencing, right? So another way of thinking about this is, anybody ever used fridge magnets and tried to put like a thick menu on to a restaurant? No? What the heck? Okay, like a laminated photo? Okay. And so you have a thicker thickness, right? And that fridge magnet sometimes falls off, doesn't it? Yeah, because you've separated your magnetic fields more by distance, and so the effective magnetic field has decreased, hasn't it? Okay? And the same thing here. So if you have more electron density, you're going to experience a lesser effective magnetic field, right? If you have less electron density, you're going to experience a larger effective magnetic field. If you have a Faraday's cage, everybody know what a Faraday cage is? Remember that cage I was talking about where you can take copper wire and you can put it around, it blocks RF signals? Okay, so if you have something like that, if you have a cage, quote unquote, something like a conjugated system, like we saw with the aromatic system before, right? Then you can block part of that magnetic field, right? And you get a smaller effective magnetic field. On the other hand, if you happen to align it the correct way to boost that magnetic field, you'd actually get a larger one, right? Is everybody starting to kind of see what's going on here? Okay, fantastic. Okay, and so our aromatic system actually had a larger magnetic field, effective magnetic field. That's actually because those align actually with your external magnetic field. Okay, whereas our tetramethylsilane has a very, very shielded core, right? Not as shielded as it can get. That's not actually the lowest possible number, in case you're wondering. But things that are more shielded would be negative numbers, right? Okay, is everybody understanding this so far? All right. Now this always changes proportionally, okay? So whatever your magnetic field external is, this will always change proportional to that, right? So for example, if you get a chemical shift with a magnet that is, let's call it a 1, since you guys probably don't know magnetic measurements very well, but we'll call that a 1, and then use a magnet that's 1.5, all of those chemical shifts would actually be the same because we're measuring everything off of TMS. Okay? That's why we do that. All right, so let's look at a proton signal, i.e. it's going to be shifted downward, i.e. to the higher chemical shift value. Notice 0 is actually put on the upward direction, right? And then we call everything from there downward. Okay? Okay. And so, higher chemical shift values, those are shifted downward. This is going to be shifted downfield by nearby electronegative atoms. And we actually saw a great example of that with methyl versus another methyl. But this one had a fluorine on it, right? And so, pretty big difference, isn't there? Yeah. And so the electronegative atom right here, what it's doing is it's actually withdrawing electrons from this carbon-hydrogen system, right? So the carbon pulls electrons from the hydrogens, the fluorine pulls electrons from the carbon. And they pull electrons from those hydrogens. Those are going to cause the electron density to fall around the hydrogens, right? And that's going to be called de-shielded because you've removed the electron density, which would have shielded your nucleus from the magnet, right? Okay. All right, and so this is going to result in a higher signal frequency, thus a larger chemical shift. If you want to see it over here, then this would shift it towards this one, right? This would be your methyls. This one would be your fluoride. So the methyl off the fluoride right here. This would just be the methyl. We've removed a bunch of the shielding, and so the effective magnetic field has greatly increased, right? Okay. So the extent of this inductive de-shielding, everybody recognizes that term, inductive? Yeah, so in organic chemistry, we had used inductive quite a bit throughout these last semester and a half-ish now. And what it is that if you remember, you can inductively, you had the inductive effect, which stabilized carbocations, right? And so carbocations pulled electron density through the sigma bond from the nearby carbons, right? And that's why like a tertiary carbocation is more stable than a secondary, which is more stable than a primary, right? That's one of the major reasons. Okay, this is the exact same effect. So again, that's the inductive de-shielding in this case because we're talking about the hydrogens. And then this is going to cause your chemical shift. And this is going to largely depend on the electronegativity. That's the most common cause. Though we also have, this is not the inductive de-shielding then, but we also have effects from double bonds. Okay. All right, so let's talk about magnetic anisotropy. This is going to describe a magnetic field that's non-uniform and is going to be responsible for most of the really, really big chemical shifts. You can get pretty big chemical shifts by like putting 3 fluorines on something, but it has to get pretty drastic that way. Okay. Most of your biggest chemical shifts are actually going to be aromatic or conjugated systems, that sort of thing. So this right here is actually a nice mental model to remember this with. So you right here, you have those conjugated aromatic pi system, right? Everybody okay with that? You've seen that plenty of times. Okay. And so your electrons are moving around within that. This motion of the electrons within that closed system is going to create its own magnetic field. Now this magnetic field actually follows the right-hand rule. And so this is actually sort of a nice drawing of this magnetic field. And what you notice is that depending how these atoms align within this magnetic field, it's either going to boost or subtract from, right? So in this case, an aromatic benzene ring is actually going to boost that de-shielding effect. Okay? It's actually going to boost your effective magnetic field. And that's why you end up with extremely large shifts. Is you actually have your localized magnetic field line up with your external magnetic field. Okay? Anybody have any questions there? Now notice that this field is going to drop off as a cube function, right? And so it's the same thing as like a gravity or a magnet when you're playing with them. So if you put magnets this far apart, you experience very little magnetism, right? They need to get pretty close to actually experience it, right? And you feel that point where it's real weak, and then you bring them closer and it gets stronger, right? And that's the sort of relationship you get with distance. And so these magnetic fields internally here, they drop off with distance really fast. Okay? All right, so this is another example of this. This is actually your alkene hydrogens. And so what you'll see here is, again, you have this a molecular orbital, the pi bond right here. It's delocalized, so the electrons are going to be moving around in it. Okay? And this is actually going to create, again, a right-hand rule off of the motion of those electrons. And so you're going to get a magnetic field here that's actually going to reinforce the external magnetic field instead of oppose it. Okay? And so you end up with hydrogen atoms that actually feel additional magnetic field. They have a larger effective magnetic field. Okay. Okay, let's look at alkynes. You may have went, hey, if one pi bond is good, then two should be better, right? But what the heck, Dr. Clausen? Look at this crap. You gave us 4.7 for this one, and then we go up here to the alkyne, 2.4. That's not as much magnetic field, is it? Something's going on. And it has to do with the geometry and the direction of your magnetic field as opposed to the hydrogen. And so in these cases right here, your hydrogens are off to the sides. See that? And so the motion is actually perpendicular to your hydrogens, right? And thus the magnetic field actually goes ahead and reinforces the pull on the hydrogen nuclei. Okay? When we look at this one here, what ends up happening is this actually ends up aligning within the external magnetic field like so. And that means that our magnetic field actually reinforces, actually opposes this magnetic field here. It adds additional shielding. Okay? Now, notice that this is actually the most acidic of the hydrogens, isn't it? So you would have actually expected this hydrogen here to have a bit less and to perhaps actually have a higher frequency, a greater shift. But in this case, because of the localized magnetic field, these actually cause a opposing of that external magnetic field. Okay? And so you experience quite a bit less shift than double bond would. Still more than a CH3, though. Okay, and so this right here is an increasing number of electronegative atoms. So here we have just the methyl, and then we go ahead and change hydrogens to chlorines so we can see what sort of effect they have. And so we put one chlorine on it, and it goes from a 0.9 to a 3.1 chemical shift. Okay, the units for chemical shift are typically going to be something like a delta ppm or just ppm, right? And so we add another chlorine, and what happens to the chemical shift? Goes up, doesn't it? Yeah. Nobody's surprised by that, are you? No. We're just reinforcing the same inductive effect, aren't we? So we're making this have its electrons get pulled away from it. The carbon is having more electron density pulled away from it. It becomes more positive, and so pulls more electron density from the hydrogen, doesn't it? And so that's just the same sort of relationship we had first started with. Okay? And of course, you can go ahead and do that. You can put like multiple oxygens, fluorines, chlorines, etc. Okay? You can put a CF3 over here, and it'd really pull. It'd have a hell of a pull on it. And so you can get very large inductive effects, but individually they tend to be weaker than aromatic effects and alkene effects. Okay. All right. So let's talk about distance from it. So here we see our aromatic ring, and this is going to cause a very large deshielding because our magnetic field is actually going to align, right? And so we're going to get a very large effective magnetic field. Okay, and so we're right on it, and we have a shift of 7.2 ppm. Anybody know what small delta means, by the way? Partial differences, right? Yeah. So large delta means whole number differences, whole differences, qualitative differences. Small deltas mean partial differences. Okay, usually quantitative difference. Okay. So 7.2 ppm. We look here, we go one off of this, that'd be the alpha position, and what we see is we actually experience less deshielding from that, right? Because we're dropping off as we go further distance from it. And so we get a 2.6 ppm, still pretty elevated, but not anywhere near what you would have expected from an aromatic ring, right? And then we go one more position off of it, and we notice that we actually experience very little difference, don't we? This would normally be 0.9, but now it's only 1.2, right? And so we've dropped off the majority of that difference, okay? After your second off, your beta, your gammas usually experience basically nothing, maybe a 0.1 or so. And then after that, you experience nothing at all. And that's why the effects, you may have noticed we had like a rule that we talked about before, where like the effects of things typically dropped off after the third to nothing. Okay? So as we go along a carbon chain, that third carbon you experience almost nothing, and the fourth carbon off, you experience nothing. It's just gone. Okay? You can change that rule if you get extreme enough, but in organic chemistry, you're basically never going to see the difference there. Okay, and so we can actually estimate these by just taking them and sort of summing them together, and it'll give us a pretty close number because magnetic fields tend to add together fairly well. And so we take this right here, we start with a 0.9 ppm, and that's because that's that normal CH3 that we're messing with, right? See that? And one of the hydrogens have been replaced by chlorine. And one of the other ones here, the carbon, has been replaced by an aromatic ring, hasn't it? Okay. And so what we go ahead and do is we would add a 1.4 for this next position off an aromatic ring. And then we'd add a 2.2 from that table for the chlorine. Okay. We add those together. We find out we should get something about 4.5. And that's actually pretty reasonably close to the shift you would see in experimental. Okay, it won't be perfect. It'll be a little off. More often than not, it won't shift quite as much. Okay, but overall, it'll give you very good numbers to work from. Pretty reasonable considering you're just adding numbers off the table, which is like the easiest thing you could do for predictions, right? All right. Let's talk a bit about substitutions. So again, we have another example here where we're going to go ahead and predict a hydrogen. So normally this hydrogen here would be something like a 0.9. And so we go ahead and add a 1.2 for it being next to a double bond carbonyl. And then we go, okay, so this right here would only be a 0.2, a fifth of the 2.4 from here. And so we get a substitution effect that is that sort of difference of those. Okay? All right, so let's go and look at some substitution effects and how you can sort of figure out differences for a substituent. Okay? So if you look at the difference between the group without the substituent, and then you look at what it would be like with the substituent, you can get substitution effects. Right, so this right here is the substitution effect. For example, right here, we have this double bond going on to a CH3. Can everybody see that, the example okay? Is it showing up on the projector all right? Okay. Okay, so that's this right here. Okay, so what we would see here is normally this CH3 would have a shift that's 0.9, right? Right. So if we look at the measurement of that off of a double bond, what we would notice is that's 1.7. We take the difference between those, and that is the effect of having a double bond next to you. Okay? So that would be the effect of having the alpha position off a double bond. Is that making sense for everybody? So in all of these, you're looking at the CH3 is over here with hydrogens on it. Okay? This is then the substituent. So if you have that substituent and you have a CH3 off of it, we would add that number. Okay? So let's go ahead and look at the carbonyl real quick. You may have wondered where exactly I got my number here from. Okay? And so we look at carbonyl. We take with the substituent off of CH3, and then we reverse CH3. Okay? And so the effect of that substituent, which is a carbonyl, would be 2.1 minus 0.9. That's the 1.2 that I used up here. Okay. Okay. This is an aromatic ring, by the way. Bromine, chlorine. Here we have an oxygen going off to something else, like an H or an R. This would actually be what would be this one right here, in case you're wondering. Okay. So the hydrogen here would experience that sort of effect. So we're going to go ahead and go here. And we again look up that value off our table, 3.3 for a CH3 with that group on it, right? And then we look at CH3, subtract that off, and we get a 2.4. And that's where this number here comes from. What I then did is I took that and I reduced it by a fifth. Okay? So it's only a fifth the effect we're going to experience the next one over. Okay? Mm-hmm.
How did you know to reduce it by a fifth?
So that's actually the... if we look at the separation factor, that's usually a 20% difference in these. You can either derive that from the table, but I believe it actually says it in your book, if I remember correctly. You guys will have to check that out for me. I don't remember the exact text. Yeah.
That was 1 over.
Mm-hmm. Yep.
So if it was 2 over, it'd be even more.
Yeah. Yeah. And that's why you get that rapid drop-off. And that actually would come from magnetic field versus the distances. So the average carbon bond distance, if you take the reduction in the magnetic field, you'd find it's about a fifth. Okay. This fifth number, by the way, actually is an estimate because we're just doing, broad estimates. It would actually depend on the distance of the bond here. But if you were to take the distance versus magnetic field strength formula and do the distance for a carbon-carbon double bond, that'd be about a fifth. And so it's usually like a fifth each one. And that's why you barely get anything on the third carbon over. And you don't get anything on the next one. Okay, so let's go ahead and look at some formulas. So this actually is the quantitative examination of your NMR signal, your chemical shift, and we need to also look at deuterated solvents because deuterium can actually help us differentiate hydrogens and tell more specific examples of geometry. Does anybody know how you would deuterate something, by the way? So does anybody remember what deuterium is? Okay, and so hydrogen is 1 proton, right? That's its nucleus. Okay. What's deuterium then? Hydrogen with 2 weight, and that other one is a neutron, right? Okay. So what you'd actually do is, anybody ever heard of heavy water? No? Okay, so heavy water is water. Could somebody close that door for me? Anybody? So, thank you very much, Mark. Hydrogen is actually, so water, heavy water is deuterium that has been used to make water. So instead of having the 1 weight hydrogens on the water. You instead have the molecular weight of 2 on the water. Okay? And if you mix that with samples, remember how I was always going off on like bonds break all the time and then reform? That's actually kind of a thing that happens almost all the time. What you would actually find out is that your hydrogens would actually get replaced on the most acidic positions first, of course, by that deuterated water. Okay? And so you can actually cause signals to get shifted based on deuterating them. Okay? And so if you're wondering if like this hydrogen here is different than that one, and you couldn't differentiate them, you can actually add deuterium. All right, so let's go ahead and talk a little bit about these mathematical magnetic fields. So this right here is the delta E, that's the energy difference of the spin for a bare proton. That would actually fit this formula right here. Okay, and this would be one with no shielding whatsoever. And so what we would see here is we would directly use the B external. The units for this is actually the Tesla, and that's actually the SI unit for the magnetic field. Okay, it's not the only unit for magnetic fields, but it's the one that's always used in these. Okay, everybody good with Tesla so far? All right, fantastic. So H, does anybody remember H from anything? Yeah, it's Planck's constant. You got it. Yeah. And that's that 6.626 times 10 to the negative 34. That's joules seconds. And so that's the same thing you use for like the frequency of light. Gamma here, everybody recognizes gamma, right? Okay, not Y. Okay. This is going to be the gyromagnetic ratio. It's going to actually be a measurement of how sensitive the nuclear spin state energies are to an applied magnetic field. It's kind of like your absorptivity and the other spectroscopy calculations. It's just not actually an absorptivity. Okay? So it needs its own thing, which is gyromagnetic ratio. Okay? How sensitive the nuclear spin is to energy as applied. Each of the nucleus is going to have a spin characteristic value for gyromagnetic ratio. For a proton, it's actually just going to be 2.67512 times 10 to the 8th. This is going to, because of these other units here, actually end up with units that are Tesla to the negative 1, seconds to the negative 1. Because it has to cancel out seconds from here and Teslas from here. And that gives you joules, which is the energy there. Okay, anybody get lost in that so far? Okay, what do we get lost at?
What is the gyromagnetic ratio? Like, where does that
So
come from?
it's essentially how sensitive that spin is to external forces like our magnetic field or our energy coming in. So for a proton, which is a hydrogen, it's actually this constant value that you'd end up putting in.
Oh, okay.
Yeah.
Will we be given the constant if we're doing the same test? Okay.
Yeah. So for H and MR, it's always that value. Yeah. It would change for like deuterium, but for H and MR, it's always that value. Yeah. So the energy of your photon is going to equal the delta E of your spin for a bare proton. And that's literally just telling you the energy of your photon, that comes in has to equal that energy difference to flip them, right? And then it flips back and it re-emits that. Okay, this right here is just the substitution of this. You remember your E photon from the last chapters in general chemistry as well, and probably a few other classes. Ends up being the energy equals Planck's constant times the frequency of that light. Okay, and so we've just substituted that in here. You can notice we can actually simplify this by going ahead and dividing over H because we can cancel on both sides. Yeah. So we take the frequency of the photon, that actually equals the gyromagnetic times the external magnetic field over 2 pi. Okay. So what sort of values would you typically expect to see in these sort of things? If this is like energies of photons. I kind of gave you a bit of a hint here. So I gave you a 10 to the negative 34 number and a 10 to the 8th number, right? The gyromagnetic and the Planck's constant. Yeah. So the sort of values you'd expect to see out of this thing for energy of your photons, right? They're going to be in the 10 to the negative like 25th, right? Somewhere in that range. Okay? And so these are going to be pretty low energy photons. Specifically, we're looking at things that are usually radio waves, right? Okay. All right. This is going to be about 0.01% of the thermal energy that would be available at room energy to any of these atoms. Okay? And so what's the largest effect on this system usually? Much larger than your effect from your shooting in radio waves. Thermal, right? Yeah. So thermal is going to be an extremely large effect on these. The nuclei in your lower energy alpha spin state are going to be a small excess, but you're going to have a very small difference that you can measure. Okay? So did anybody notice on all those figures I showed you before, I had the alpha and beta states, and it was like 4 of them, and then I'd flip 1? Instead of the normal thing where I have like only a population of 1 and then I flip them all. Okay? That was why. It's because at room temperature, the thermal effect actually means you only have a little bit of those atoms that are aligned. Okay? You just increase that alpha state a bit. Right? Enough to detect, but you haven't aligned all the atoms. Okay, not even close. All right, so anybody have any questions about these so far? No? Okay, fantastic. Okay, let's talk about operating frequencies. So the operating frequency here is going to be the signal that would be produced by a bare proton. That's going to be represented by this frequency here. It looks like a little V. And then OP, which is operating, right? And so operating frequency. This is going to be the operating frequency of your spectrometer. This has to be equal to the frequency of the absorbed photon. And so substituting your operating frequency for your frequency of your photon in the equations above, this is going to give you this right here. Notice I've went ahead and substituted in the gyromagnetic constant right there and our Tesla of a typical instrument. And then these values are just constants right here, right? Okay. All right. So again, that gyromagnetic is going to be a constant. It's going to be the VOP, the operating frequency is always going to be directly proportional then to the external magnetic field. And so by changing the external magnetic field, what do we directly proportionally change and control? Operating frequency, right? So we actually have almost complete control over the operating frequency because that changes directly proportionally with our external magnetic field, right? Okay. And so we can select for that. So for example, we can apply a fairly standard external magnetic field that we've selected in this case to be 7.046 Teslas, which is what we substituted in for here. Does anybody know what 1/seconds is, by the way? Yeah, it's hertz. Yeah. So oftentimes you're actually going to see this represented in hertz. If we were to look at hertz, we can actually call that megahertz. Anybody ever recognize that? Megahertz. Yeah. The units typically used for most of the frequencies in your life. And for example, gigahertz is the signal in your Wi-Fi. Then megahertz is most of the electricity is used for like electricity, right? And so that's the typical radio wave frequencies. And so megahertz is going to be 10 to the 6th hertz. And so this is actually like 300 megahertz, right? Okay. And so what would you call this instrument, by the way, that has a Tesla field of this? You'd call it a 300 megahertz instrument. Yeah. So this is a 300 megahertz instrument because this is the sort of minimum number we need for these things. And you typically can do 300 megahertz and just vary that magnetic field by a little to pick up each different shielding state for those hydrogen nuclei, right? If we didn't have a hydrogen nuclei here, then we would need a different operating frequency, wouldn't we? Okay? And that means we need more powerful magnetic fields. So this one would be an instrument that's specifically used for hydrogens. Okay? It's an HNMR. If we wanted to do something like a CNMR, where we look at carbon nuclei, that's going to require a stronger magnetic field because this number here is going to change. Okay? Usually like a 600 megahertz instrument. All right. So let's talk about chemical shift now. Those were those ppm or delta. Both units get used fairly often. You, in fact, can see them in your book. We'll do this a lot too. Just change back and forth constantly. Okay? Because they're synonymous. They're same thing, right? Delta meaning shift, chemical shift, ppm being units. Why is it called ppm? What does ppm normally stand for? Parts per million, yeah. And it is a parts per million number. Yeah. So that's why it's called ppm. So formally, you're going to measure these in parts per million. You're going to use this, which is the frequency of your sample minus the frequency of TMS, excuse me. Need water. And that would give you the shift, right? So that's the shift part. And then you're going to divide it by the operating frequency. For our earlier instrument, that was this right here. That was our 300 megahertz instrument, right? Okay. Okay. And so a proton's chemical shift is always the same regardless of the NMR instrument used because it's standardized against an internal sample and the instrument strength, right? And so it doesn't matter if you use a 600 megahertz instrument. This would change here, here, and they would change proportional to this. And so you'd get the exact same ppms out. Okay? And that's why we use this formula to measure these things. And you use chemical shifts. Everybody okay with that? Fantastic. Fantastic. Okay. Anybody getting lost on that so far? Okay, let's talk about deuterating solvents. So, we have a kind of baseline that we built up now, right? Of why these things shift, what causes those, how are we getting these different signals come out, okay? Recall that our NMR spectrum is typically acquired using a solution. This is going to contain a very small amount of sample. You would not put in a dry powder. It's a little sample vial, okay? And you'd levitate it on air. So just a bit, very thin sample vial that's about that long, okay? And then you'd put that in, and it would be dissolved in solution, okay? So most of the solution is typically going to be a solvent whenever you're doing these spectra. So if your solvent contains any protons, then your HNMR spectra would actually be dominated by that solvent signals, okay? So that would be a problem, wouldn't it? All right? Does it make sense to try to like look at the sky over there through the wall? Why is that? Because the wall absorbs all the light you're trying to see with, right? If you could see in the radio wave frequency, wouldn't matter, would it? Those would be fairly clear. And so why do we look through a window? Because they're clear. They don't change our signal much, right? Okay. And you got to do the same thing here. So if you were to use normal solvents, like water, like alcohols, like most things that you would want to use, they would have hydrogens on them. You'd have a bunch of signals from that, and then you'd have to try to pick out between those, right? Almost everything I just mentioned would show up in places in large peaks, because it's majority of your signals can be from solvent, and they would cause incredible issues actually reading your spectrum. And so what you can actually do with this is you can replace your proton spectra with something that's going to show up in a different place and be much harder to actually see within your spectrum, right? Specifically, you're going to replace it with deuteriums. Now, this is going to cause a problem, like I had mentioned before, isn't it? So if you have any acidic protons that can break off fairly easy, what do you think is going to happen to those protons if you put them in with heavy water, like deuterium? There's a very high chance they're going to get replaced, right? Okay, so you do have to watch out for that. So for example, the carboxylic acid I showed you before is actually a bit of a challenging thing to get a good signal for, okay? Because it's acidic, and so that hydrogen gets swapped out with the deuterium, and that peak will actually go away. So if you were to throw your sample together, get it in there real fast, you would actually see the peak go away over time as that acid had its deuterium traded in for the hydrogen. Okay, but many cases that just doesn't matter much. For example, CH3, CH2, not very acidic, right? Very, very low acidity. So over a long enough period of time, you would get some replacement, but not within the time you would run a spectra, right? You'd have to really let that wait, right? To even get any replacement at all. Okay, so again, everybody's comfortable with deuterium, 2H, hydrogen with a weight of 2, has an extra neutron. Okay. The deuterium is NMR active. It has odd numbers, right? So it is NMR active. Okay. Just remember that the frequency is going to be quite a bit different than hydrogen because this number up here is going to be different for deuterium. Okay. And so we shift it out of our window and we can't really see it where we're looking. Okay, so often there's going to be a small residual solvent peak for the small amounts of solvent that end up not deuterated. Whenever we're looking at a heavy water sample, you may have noticed that nothing's 100% pure, right? We look at my bottles and even some of the stuff is 99.9999%. That still means we'd have 0.0001, right? And if you're looking at your solvent, that's still going to be a pretty significant peak, right? And so when you're using your heavy water solvents, you're still going to see a little bit of your solvents, okay? Now, having said that, I've been saying heavy water a lot. You don't have to just use heavy water, okay? You can use deuterated solvents of organic solvents. They make things like deuterated methyl. Okay, it's just very expensive if you use that stuff. So most of this is going to be done in things like heavy water. Right. Okay, let's go ahead and look at the integration of your signals. So when you're looking at signals that have width to them, okay, that have multiple things going on, your height of your signals actually is not a direct measure of your populations, right? And NMR typically has some width to it. It's going to have some splitting going on and some width to these things, okay? And so that area that's under the absorption peak, this is proportional to the number of protons that are generated this peak. Okay, so if you saw something with 3 times the area under the peak, it would have 3 times the number of protons, right? What is not true is the heights. Just because the height of the peak is 3 times does not mean it's 3 times the number of protons. Okay? It is the area. You got to be real careful about that. Right? And the problem here is, let's say that one person pays in $5, then we have $5, right? But if 3 people pay in $2, $3, two, two, and 1, well, we'd see those split, right? We'd still have $5, but we need to group them up first, don't we? And that's why you have to do the integration. Okay? Okay. Now, having said that, back in the day, you'd have to do the height versus the width, and then you'd have to do calculus, and you'd figure out the integration, and it'd be a pain in the butt. This is way before even my time. I never had to do any of that. If you do a modern instrument, it will actually integrate all of these within a second, and you can actually just put up a mask that will show you the integrals. Okay? And so then it's going to give you all the areas under the peaks, and you can just have those numbers, right? And that's what you'll see for modern day instruments. It's very nice, right? The integral trace for your single peak is actually going to give you this staircase right here. That's actually the integral trace here. So as you go along the peak, you'll notice that you actually get an increased area under it, right? And that just adds up, and that continues adding, but slower, doesn't it? And that's your area under this peak. And so that's how they actually do this. They just continuously add the numbers as they go along. And that gives you this trace right here. Yeah, it's kind of a clever way of doing it, right? Because computers, it doesn't matter if it has to count 1,000 times, does it? It can do that within microseconds. Humans, we can't do that way, can we? Yeah, it'd take us too long. So, pretty cool way to solve that. And so this is actually your integral trace right here, and you can actually just directly measure the distance here. And that would give you your height, your areas under these. Okay? And it's a much superior way to do this, because what you can do is, let's say this had been broken up over an area, well, you can just go from one side of it to the other, can't you? Yeah, it makes it real easy. So it's actually a brilliant way to solve this problem. Really cool. All right. So this right here, this would be your integral right here. And so we would measure this. This one actually represents 4 protons right here. And so there's actually this peak here is from 4 of the protons. This one right here then represents 6. Okay. And you can see here this one probably is this one's the TMS right here. Okay. Anybody have any questions about that right there? All right, so let's go ahead and talk about some splitting here. So you may have noticed that we haven't really mentioned what happens when we have these other hydrogens next to these things, right? So you may have remembered when you have bonds that can line up next to each other, they interfere with each other, right? And we had actually done that. We had used that same principle when we were talking about carbocations, didn't we? Where your orbital of your carbocation can line up with another orbital and pull electron density over, right? So these hydrogens here actually affect this hydrogen right here, okay? And this actually causes this signal here. This is the zoom in. Can everybody see that okay? Okay, you okay? Okay. Can everybody see this right here? How many peaks are there? 3. How many hydrogens are there? Right here. Yeah, this is this one's peak. So it only has 1. And what's happening is these hydrogens over here are actually causing that to split. Okay? And it's the n+1 rule. So this is splitting your signal. This is called spin-spin coupling. What's happening is the spin state of this hydrogen is coupling with the spin state of these hydrogens right here. Right? And so the more spin states you have next to it, the more peaks you're going to see here. Specifically, it would be 1 plus the number of spin states over here. Okay? So again, that's your signal splitting. It's going to be pretty much ubiquitous unless you only have a hydrogen, nothing next to it, right? most molecules have hydrogens next to each other, on the carbons next to each other. Okay, so again, what do we notice about where this hydrogen is versus this one? The cis trans won't matter in this case, but what they are is the one next, right? Okay, so they're the one on the carbon next to it. Okay, those cause splitting. Let's look at these real quick so we can make sure we break a pretty common misconception that develops. Okay, so these ones have two hydrogens right there, right? Okay, and chemically they'd be identical. Right? But we see a split it, don't we? We see two splits. Okay, so that has less split states though, doesn't it? So a common misconception, and get your minds in the this is wrong, don't do this state. Okay? Like super common misconception, even after I say this, there'll be like a fifth of the people that will have this thought pop up in their head. Okay? Okay, so you ready for it? Not true. Okay? Everybody ready for not true? Okay, so the hydrogens that are on the same carbon do not influence the spin state. They are not spin-spin coupled. Okay? So what people do is they all the time flip these things. So when you want to find out how many splittings are going to happen, how many states we're going to be in, you would look at the carbon next to the one you're looking at. So you're looking at these hydrogens here to figure out how many splits this would be. It's not this carbon you look at, it's the one next to it. And that has one hydrogen, and so that's 1 plus 1 gives you 2. Okay? And for this one, when we're looking at this one here, you would look at the one next to it. And so that is 2 plus 1 gives you 3, right? Okay. Everybody got that? Okay. Everybody got that wrong thought purged? We're going 1984 with our thought talk. All right. Anybody have any questions about this so far?
So what you just said was not true.
Okay, so what I just said was, okay, let's do the true one, okay? Okay. So, when we're looking for the splitting that happens on this hydrogen set right here, okay? Where do we look? The carbon next to it. That is correct. Okay? So, the things that cause splitting for your bar magnet is not the magnet itself, right? Think of these as little magnets that are spinning in space, right? Okay, you got your little magnets spinning in space. And so if you had two magnets near each other, what would happen? Yeah, they'd start interacting, right? And that's what you're seeing here. But the magnet itself doesn't hurt itself, right? Doesn't do anything to itself. Okay? So these don't do anything to each other because they're too close. They're the same spin state. Okay? These ones over next to it are going to interfere with that spin state. And they're going to cause just little tiny interferences. And that's just why these are so close. And that's your spin-spin coupling. Is that making sense? Okay. So again, the correct thing to think, ones on the that are the same chemically, don't interfere. Ones nearby that are different chemically will interfere. Okay? Okay. All right. Hmm?
What if there were 3 carbons? Which one would we go to, or do we do both? Like if there was a third carbon and we were looking at the middle.
If this was hydrogen? Oh, another carbon here.
Yeah.
Yeah, we do both.
Okay.
Yeah. Yeah, so if this had like a reflection over here, that's the same thing, you'd have an extra spin. Yeah. And so that would be 1, 2, plus 1. Yeah, we'll see some examples in just a bit. Okay, so let's talk about the n+1 rule real quick. If proton A is coupled only to proton B and there are n equivalent protons B, then proton A is going to have n coupled protons. The signal from proton A will be split into n+1 peaks. And so let's look at that coupling. So the number of coupled protons that are chemically distinct nearby, this is going to give you this n number. If there's nothing nearby, that would be 0, right? The case we just looked at was 1. And if we had another one over, like on the other side, that was chemically distinct, that would give you another one, which would be 2, right? Okay, so the number of peaks you're going to see in the splitting pattern would always be n+1. Okay? Essentially, it's the options of it being coupled or non-coupled, right? So you got the nothing really happens to it, and then it's pulling it this way, pulling it that way. Okay? Okay, so a single peak is going to be called a singlet, abbreviated S. A double peak would be called a doublet. 3 peaks, triplet. 4 peaks, quartet. You guys all probably recognize this language, right? Okay. And that's Q here. This is quintet, 5. And if you get past 5, just call it multiplet. Nobody counts past 5. It's already impressive that chemists went past 5. We usually only go up to 3, right? Yeah. This would be your relative peak heights. So if you have a singlet, you're going to have 1 peak, and it's the whole height, right? If you have a doublet, they're going to be 1 to 1, and they should be even. Okay. If you have a triplet, you'll see the peaks on the side will be about half the strength as the one in the middle. Okay. And we can actually see that right here, right? Remember, it's the integrals area that you're looking at. These are about even. This one in the middle is stronger than the other two, right? And so then a quartet would look something like that. 1, 3, 3, 1. And then quintet would be 1, 4, 6, 4, 1. Okay. So remember again, these are always, this n number is not the number of protons that generate a signal. This is actually one of the places that's very different from like absorption spectra and all that sort of stuff, right? So in here is always the number that's coupled to those protons. It's the other protons around them, not the protons that make the signal. Okay? Okay. So it's a very, very common place to get messed up here. So like underline, exclamation points. Okay? All right, so let's look at some equivalent protons and show you, like, for example, why I was using that very specific terminology, right? I was really, really careful on that terminology. And so right here, these protons right here, they are equivalent, aren't they? See that? Because it's symmetric, isn't it? And so what ends up happening is these actually have these same spin states. So they can't couple. So these are chemically equivalent protons. Did you guys catch that when I was using the same terminology as I'd used before? Chemically equivalent, that they're the same, symmetric, same protons, right? Okay, and you may recognize this from our previous figure here, because we'd actually been talking about this as the 4 protons here, 6 protons there, and the integral, right? And you saw that it didn't really have any width to these things, did it? Yeah. Okay. These would actually be your chemically non-equivalent protons, right? So these ones here are chemically non-equivalent. But what do you notice about the next carbon over? No protons. No splitting, right? Yeah. So we got an example here of non-splitting, right? Yeah. Okay. So think about this problem, and we'll answer it next time. Okay. Ooh, I could make that into the plicker. Yeah. Save my brain for once. I always have to come with those plickers like last minute before because I have no time. Huh? Yes, you did. Yeah, my computer for some reason said it was extended, and it was not, was it? Yeah. You all have a wonderful day. I'll see you all around. Don't forget the lab reports, right? Make sure you get those in. Formal lab report.
Is the exam Monday?
Yeah. What? How far did we get?